Good morning, everybody. I'm going to be honest, this is my third time I have attempted to record this note video. The first time, it didn't record. Second time, the audio didn't record. So here's hoping that this one actually works out. Let's dive right in. This is 9.3 quantitative energy. So we are going to be calculating all of these types of energies that you see, except for thermal energy, but we're going to talk about it nonetheless. All of this is under the umbrella of conservation of energy. So let's dive right in. First thing is translational kinetic energy. Now, we haven't seen that word translational before. All it really means, guys, is something that is moving across a distance. So that could be moving this way, that could be moving up. Anything that is moving a distance is translating. Now, translational kinetic energy is dependent on two things. It's dependent on the mass of the object and the rate that it's moving at, or its velocity. So m is mass, v is velocity. Those are in kilograms and meters per second, as always. And k is in joules, as all of our energies are going to be. So this tells me that something that is moving fast is going to have a high kinetic energy. Something that has a high mass is also going to have a high kinetic energy. All of that should be fairly intuitive. Rotational kinetic energy refers to the kinetic energy of something that is spinning. Okay, so think about your car. Your car is translating because it is moving across the ground, but the wheels have rotational kinetic energy. So your car would have translational kinetic and rotational kinetic. Rotational kinetic energy is dependent on I, which is the moment of inertia, or kilogram meters squared, and omega, which is the angular velocity measured in radians per second. So yes, we're going to be bringing back circular motion stuff. I know you guys are thrilled about that. Moving on. Gravitational potential energy. This is stored energy due to the position of an object. Real easy, guys. Something that is higher than something else. Let's say that there are these two things here. They both have the same mass. Number two is going to have more gravitational potential because it's higher. Let's say that, again, I've got two objects, except object number 2 is much more massive than object number 1, and they're at the same height. Well, 2 is going to have more gravitational potential because it has a higher mass. All right, m is mass in kilograms, g is 9.8 meters per second squared, and h is the height in meters above the ground. All right, stored energy due to the position. Let's talk about elastic potential energy. So elastic potential energy is stored energy due to the compression or stretching of a spring. So you could have, if this is our equilibrium, you could have something that has been compressed a distance x, or, again, here's our equilibrium, something that has been stretched a distance x. All right? Now, does it matter if x is positive or negative? No, because it's squared. All right? So US is our elastic potential energy in joules. K is the spring constant, which, remember, that's just an inherent quality of the spring. So that would be something that is given to you. And then X is the distance that it is stretched or compressed from equilibrium. All right? Now, how do we use all of these things together? Well, we recall that the change in energy of a system is referred to as the work that is done. Remember, think of that in bank terms, where if I have my system here, all right, and in my system I've got rotational energy, I've got translational, I've got potential energy due to gravity, I've got the spring energy. Anything outside of this is work. Now, work is done by external forces. So inside of this, I can still have forces, but those are just referred to as internal forces because they're not going to be doing work on my system. All right? Now, if there are no external forces, well, then no work is done. That's an ideal situation because then I don't have to solve for work. Luckily for us, guys, we can make it that way if we pick the right system. So for an isolated system, the energy at the beginning is going to be equal to the energy at the end because the total change is 0. Now, does that mean that all of these energies are constant the entire time? No. Think of this as, let's say that I have my checking account, and my savings account. And I transferred all of my money from my checking into my savings account. I still have the same amount of money, but I've moved it from one location to the other, all of it still staying in the bank. All right, so I'm just changing the location that energy is being stored. All right, so let's look at some situations here. Let's say first I have an object in free fall. So what we want to do is we want to select a system that includes as many forces and as many types of energies as we can. So here, what I'd want to do is I'd want to select my system so that there are no external forces. The way that I'm going to do that is by putting the ball and the earth all in the same system. No external forces. All right? Over here, I want to do the same thing. In my system, I want to have no external forces. Therefore, the object, the ramp, and the earth are all going to be in there because there I've got an object sliding down a frictionless ramp. Here, I've got an object compressing a spring. So, we're going to have the object, not there. We want it in the system. Here's our system. We're going to have our object and our spring. All right? Everything in the system that we can calculate energy for. All right? Let's talk about how to problem solve with this. So you want to draw a before and after visual. As always, you want to apply the conservation of energy. So we want to set up an equation for it. And then we've got to think about, is work being done? And that is entirely dependent on what your system is. So if you've got things like friction outside of your system or air resistance, anything that is going to be stealing energy, work is going to be done, all right? If the system is isolated, if all of the energies are in there, then no work is done. Then you're going to make substitutions for equations, solve for corresponding variables, and get to your final answer, all right? So those are the notes. I'm going to have separate videos for the examples, and then you guys can get to the problem set, all right?